Welcome to Pastor Victor's Academy. Embark on a journey through the world of engineering mathematics and electrical engineering with our educational tutorials designed specifically for engineering students. Whether you're mastering calculus, solving complex circuit problems, or exploring power systems, Pastor Victor's Academy is your ultimate learning companion. Join us as we break down complex concepts into clear, easy-to-understand lessons, helping you build the foundational knowledge and skills needed to excel in engineering mathematics and electrical engineering courses. Subscribe now to kickstart your learning journey and gain the confidence to tackle engineering challenges head-on. Let's unlock the world of mathematics and electrical engineering together, one lesson at a time.
Good day, welcome to Pastor Victor's Academy. It's nice having you here. In my previous video, I talked about vaporization processes of pure substances. In this video, I want to talk about retrieving thermodynamic properties using the property table. So please pay attention as we go on. You'll be learning a lot from this video. Don't be distracted. Pay attention as we continue. A property table is a table that contains the thermodynamic properties of a substance at various equilibrium conditions of pressure, temperature, and phase. Take note of the word equilibrium. So what the property table does is to provide us with information about the properties of pure substances at equilibrium states. And the properties can be pressure, temperature, specific volume, internal energy, enthalpy, and entropy. So for the pressure, we have the symbol P. For the temperature, we have T. For specific volume, we have small v. Then we have U for internal energy, H for enthalpy, and S for entropy. So I want you to note that H is equal to U plus PV. So where you are not given H in the property table and you have U, you have P, you have V, you can simply get your word H by using this formula. Now, we have VF, we have VG. This is the specific volume when vaporization begins. This is the specific volume when vaporization ends. This is the internal energy when vaporization begins. The same thing when vaporization will end. So that's the same HF, SF, HG, SG. So this part is for the beginning of what? Vaporization. Whereas this part is when vaporization has ended. So you will see these symbols on the property table. P for pressure, T for temperature, V for specific volume, U for internal energy, H for enthalpy, and S for entropy. The values of the extensive properties are always given in per unit basis. So what does that mean? Now, normally volume has capital letters, the symbol. Then this is capital U, this is a capital H, and this is capital S. But when we begin to work with per unit basis, then capital V becomes small v, capital U becomes small u, capital H becomes small h, capital S becomes small s. So these ones are in per unit mass basis. But pressure is an intensive property, so it's not in per unit mass. Likewise, what? Temperature. It is not in what? Per unit mass. So here are some examples. Specific volume, meter cube per kilogram. So this is in per unit mass. Then here we also have meter cube and kilomole. So here we are having kilogram, that is mass. But here we are having kilomole. Then internal energy, kilojoules per kilogram, kilojoules per kilomole. Then entropy, kilojoules per kilogram per Kelvin. So you can see that it's in per unit what? Basis. And that thing is that different property tables adopt different unit system. So when you get a property table, do well to look at the units of the properties, because what you have as units in one property table may not be what you have as units in another property table. For example, the unit of pressure can be Pascal, can be Newton per meter square. So one property table may decide to use Pascal as the unit of pressure, or megapascal. Then another property table may decide to use what? Newton per meter square. There are other units of pressure. So it just depends on the property table you are working with. Know the unit system it is adopting. You get? Then another example is temperature. We can have Kelvin, we can have Fahrenheit, we can have degrees Celsius. So it just depends on the property table you are working with. The next thing is that property tables are organized based on the phase of the substance. So the first one is that we have the compressed liquid table. That's for compressed liquid. It's also called subcooled liquid table. Then we have the saturated mixture or liquid vapor table. Then the other one is the superheated vapor table. So these are the three major tables we have. So we want to look at how the values of properties are retrieved from the property table. Now the first challenge is knowing the table to use, whether to use the compressed liquid table or the liquid vapor table or the superheated vapor table. Now how do you solve that problem? Number one, know the substance in the system. So you have to know the substance you are working with. Is it water? Is it air? So just know the substance you are working with. So if you are working with water, that means you should go to what? Water table. If you are working with air, you should go to the table that has the values for what? Air. If it is refrigerant, go to table for that particular what? Refrigerant. That's the first thing. Then the second one, know the phase of the substance. Now, why is this necessary? As this will help you to know the table to use. You have to know the phase of the word substance, whether the substance is in compressed liquid phase, liquid vapor phase, or superheated vapor phase. You have to know that so that you can know the exact table where you can get your values. Now, how do you know that? When T is less than T sat of P, compressed liquid table, or when P is greater than P sat of T, then you'll still find your values on compressed liquid table. So what that means is that the first place to go to is your saturated or liquid vapor table, because that's when you can know if T is less than T sat or P is greater than what? P sat. Please take note, sat is a short form for saturation. So T sat would mean saturation what? Temperature. So we want to use water as an example. At a pressure of 1 atm, the saturation temperature is 100 degrees Celsius. So when we go to the liquid vapor table, we will discover that for 1 atm, we must have 100 degrees Celsius. So how do we know if our values will be in that saturated or liquid vapor table? Now we will check if our T is less than T sat. So T sat is 100 degrees Celsius. That's if pressure is already 1 atm. Remember that we stated that for a particular pressure. So if we are working with pressure of 1 atm, and now we've known that for a pressure of 1 atm, T sat is 100 degrees Celsius. Now we check the temperature we are given or we are working with. Is it less than 100 degrees Celsius? If the temperature is less than 100 degrees Celsius, what it means is that we cannot get our values on that table. That's the liquid vapor table. So we'll move to compressed liquid water table. That's where our values would be, because T is less than 100 degrees Celsius. The same thing applies. If we fix our temperature at 100 degrees Celsius, that means our P sat will be 1 atm. So what we do is to go to any of the liquid vapor tables, look for T of 100 degrees Celsius, then check the P sat. The P sat will be 1 atm. Then the pressure we are given or we are working with, we check if that pressure is greater than P sat. Remember our TV diagram and PV diagram. For TV diagram, we start from lower temperature to higher temperature, but for PV diagram, we start from higher pressure to lower pressure. So P has to be greater than P sat for us to be in compressed liquid water region. So in that case, if P is greater than P sat for this temperature, 100 degrees Celsius, that means we leave that saturated table we move to compressed liquid what table. That's where our values would be. Then, if T is equal to T sat of P, now P, we say let P be 1 atm and T sat of P is 100 degrees Celsius. So if our temperature is 100 degrees Celsius, so there's no point leaving. That's where our values would be. So it shows that the substance we are working with is in a saturated what state, or is in the liquid vapor phase. So that's it. Then if P is also equal to P sat, that's what it means. So it means we are working with saturation values, and in that case, we will remain on the liquid vapor what table. Our values would be on the liquid vapor table. Now, the third case is if T is greater than T sat. Remember your TV diagram, this can only be possible when we have entered the superheated vapor region. For T to be greater than T sat, you get. So in that case, when we have fixed pressure at 1 atm, we know that T sat is 100 degrees Celsius. So we are checking if the temperature we are working with is greater than 100 degrees Celsius. If it is greater, we leave this part and we move to superheated vapor table. Our values will be there. The same thing applies to the pressure. If the pressure is less than P sat for this 100 degrees Celsius, then we leave here and we'll come to here. Our values must be on this word table. So that's how to know the table where you can get the values for properties. So the next problem we want to solve is fixing the state, because it is not enough to know the table you are to work with. You should also be able to fix the state of the system to enable you find the values you're looking for. Now, to enable you to do that, we say for single phase regions with P and T, you can fix the state. So if you're in compressed liquid region or superheated vapor region, what you just need to know is the pressure and temperature. You can fix the state. So where the pressure column and the temperature column intersects, that gives you your what? Your state. And that enables you to get your values. You can as well fix the state using pressure and specific volume. So if you are given the specific volume, then you know the pressure, you can fix the state. So where pressure and specific volume intersect, that becomes your state. The same thing applies to this. With temperature and specific volume, you can also fix the state of the system. Now, for two-phase region, P and T cannot fix the state. You will need X, and X is called quality, because P and T are no longer independent values. So what that means is when you know T, you can tell what P is. When you know P, you can tell what T is. That means for every P, there is what? A particular T. While in the two-phase region, P is constant and T is what? Constant. So in that case, there is no particular point on this line where we can call the state of the system. Because on every point on this line, we are having the same pressure and what? Temperature. And what we are looking for is just a point. That's the state of the system. So we will need something else that can help us solve the problem. And that can be P and V. So with P and V, because pressure can intersect with what? V at a particular point. Or with T and V, temperature can also intersect with what? V at a particular point. You can fix the state. But when you want to work with P and T, you will need another property, which is called what? Quality X. So when you know X, and you know P, and you know T, then you can be able to fix the state of the system. So what X does is to tell us the exact point on this line that represents the state of the system. So X will tell us whether we're on this point, on this point, on this point, or here. So here X is 0 and here X is 1. X has no unit, it's a ratio. It ranges from 0 to 1. Here's the formula for X. Mass of vapor over total mass. You know, when liquid is changing to vapor, it's a gradual process. Everything does not just change immediately. So as it is changing, the mass of vapor formed at that moment divided by the total mass. That's total mass here includes both the mass of vapor and mass of liquid. So it's a ratio of the mass of vapor to the total mass, and that gives you your what? X. So when you know P and you know T, with X, you can now fix the state of the system. But when X is not there for you to work with, probably because information about the mass is not there, a specific volume should be given so that with specific volume and pressure, you can fix the state. Or with specific volume and temperature, you can also what? Fix the state of the system. Now, another thing is that for compressed liquid region, V of T, P, that's V at a particular temperature and pressure, is approximately equal to Vf of T. So what that means is that if you want to find the specific volume of a compressed liquid at a particular temperature and pressure, and let's assume the compressed liquid table is not given, you can go to the liquid vapor table to that exact temperature and pick your Vf. That's what it means. So your Vf for that exact temperature is approximately equal to your V for T, P on the compressed liquid table. Now, why is that so? The volume of liquid does not change significantly with changes in what? Pressure. So if you look at the PV diagram, this line is almost a vertical line. So indicating that the change in volume from here to the point of saturation is very small. Vf is the volume at point of saturation. Then we have a constant temperature here. So remember that the temperature here is the temperature here. That's the temperature for every point on this line. So we can say that V is approximately equal to what? Vf. But in the case of TV diagram, P is constant. That's a constant pressure process. Now, the change is significant. So we cannot approximate, else we introduce what? Error into our work. So temperature affects the volume of compressed liquid more, unlike pressure. The effect of pressure is usually insignificant. That's why we can ignore pressure and just work with the temperature. We just collect the temperature, go to the liquid vapor table, look for the same temperature, and collect your Vf. It's almost the same value. So for example, let's look at this. These are values for water. Now, specific volume at 100 degrees Celsius and pressure of 2 atm is equal to 0.001042 meter cube per kilogram. So here pressure is 2 atm. Specific volume at 100 degrees Celsius and pressure of 1 atm is equal to 0.001043 meter cube per kilogram. And remember that these are saturation values. So in that case, this is Vf. So Vf is 0.001043 meter cube per watt kilogram. Now check the difference. We ended with 4.2 here. We are ending with 4.3 here. So you can see here that the difference is what? 0.000001. But look at this one. V at 99 degrees Celsius and 1 atm, and V at 100 degrees Celsius and 1 atm. So pressure is held constant. In this case, temperature is held constant. Let's see what happens. So for this one, we are having 0.001041 meter cube per kilogram. But for this one, we are having 0.001043 meter cube per kilogram. So you can see that just a unit difference caused what? A larger change. So the change in volume here is double of the change in volume word here. So this gives us a better what? Approximation. That's when temperature is held constant. Now, another thing you need to know is that for the saturated region, specific volume V is equal to Vf plus X into Vg minus what? Vf. Remember your Vg is the specific volume on the saturated vapor curve, while your Vf is the specific volume on the saturated liquid curve. That's at this point quality is 0, at this point quality is what? 1. So what we have is that V is equal to Vf plus quality into Vg minus what? Vf. So the same thing applies to enthalpy, internal energy, and entropy. HF plus X into Hg minus HF, UF plus X into Ug minus UF, SF plus X into Sg minus what? SF. Some property tables can give you this: Vg minus Vf, Hg minus Hf, Ug minus Uf, and Sg minus Sf. So that's when you begin to see VFG, something like that, either VFG or VGF. So it's giving you the value of the difference between Vg and Vf. Again, if your property lies between two tabulated values, interpolate between the two known points. Let me explain what that means. Normally, if this is a straight line graph, you notice that the slope will be the same at all points. So with the idea of the slope being the same at all points, and we know that the slope is equal to y3 minus y2 over x3 minus x2, which is also y2 minus y1 over x2 minus what? X1. So this is slope, this is what? Slope. Any of these can give us the slope of this graph, since it's a straight line graph. Now, equating the two slopes is what gives birth to this: y2 minus y1, x2 minus x1, y3 minus y2, x3 minus what? X2. Now, what happens is that on the single phase regions, within a very short interval, we can treat the points as what? Being on a straight line. Okay, so since we are treating those points as being on a straight line, the slope is constant. So that will help us to find a value that is in an intermediate what? Position. Take for instance, you know T, you know T1, you know V3, you know V1, but you know T2 and you don't know V2, or you know V2 and you don't know T2. How do you get the value of T2 or V2 depending on the one you know? You simply say T3 minus T2 over V3 minus V2 equal to T2 minus T1 over V2 minus what? V1. So notice what I did. The one I'm looking for must be the one at the middle. So it's either I'm looking for T2 or I'm looking for V2. Then I'll use these other values to do my work, interpolation. So what I'll do here, if I'm looking for T2, I make T2 the subject of the formula and I get the value for my T2. If I'm looking for V2, I make V2 the subject of the formula and get the value for my V2. So with these two values and two values, I can easily get an unknown value, whether it be T2 or V2, as long as either of them is known. So that's what interpolation is about. So finally, when you want to get the value of a property on the property table, ensure you are working with the units on the property table. Otherwise, convert to appropriate units before retrieving properties. Now, take for instance, you have your pressure in Pascal, but on the property table, the unit of pressure is given in megapascal, as MPa. You will not say, since I have in Pascal, let me just go into the property table. No. Convert your pressure to what? To megapascal. Then that will help you to easily locate where your pressure is on the property table. So ensure that the unit you have is consistent with the unit on the property table before you begin to work with it. And for the extensive properties that are given in per unit basis, when you start working with it, know what you want. If your answer is supposed to be in per unit basis, that's fine. But if your answer is not supposed to be in per unit basis, then multiply with the necessary value to give you the actual value for that particular quantity of matter you are working with. So with this, we've come to the end of this video. I believe you've learned a lot and you enjoyed the lecture. Thank you so much for watching. Please do well to like, do well to share, subscribe. Tell your friends about Pastor Victor's Academy. If you know that what I'm doing here is good, tell people about me. Share the link and subscribe. Once again, thank you so much for watching. God bless you.